Welcome everyone. Today, this is Gianni Antichi, and today I'm gonna introduce you to Mehmet Sahiin, that received his PhD in information system from Gazi University. He's currently a system and network administrator at the Scientific and Technological Research Council of Turkey, and a part-time postdoctoral researcher at the Wireless System Network and Cybersecurity Lab in the Department of Computer Engineering at Matthew University. His research interests focus on networking, cybersecurity, software-defined networking, and programmable data plane. And today he's going to talk us about his recent research about Bloom filters and network security and programmable networks. Thank you very much, Mehmet, for being here, and the stage is yours.
Okay, thank you, Gianni, for the kind introduction. And hi, everyone. My name is Mehmet Emin Sahiin, and today I will be presenting high-accuracy updatable Bloom filters for robust network security in programmable networks. In this talk, I will introduce the motivation behind using Bloom filters in network security, explain the limitations of original design, and then describe how our proposed model overcomes these issues. I will also walk you through several use cases why this model appears as a strong candidate for deployment in programmable data planes. Okay. Programmable data planes are powerful in terms of flexibility, scalability, and line-rate packet processing. On the other hand, they offer limited memory space due to high-cost restrictions known as TCAM or SRAM. Especially stateful network functions like flow tracking, firewall, or load balancing become hard to implement as they require memory-intensive algorithms on data planes. Therefore, there is a need for space-efficient algorithms on data planes. On the other hand, Bloom filter is a probabilistic data structure that works space-efficient and enables fixed query time. Using a Bloom filter, it can be queried at a low cost whether an element is in a set or not. So it becomes attractive to use on data planes. However, it may generate false positive results. This is the main challenge of using it. The use of Bloom filters on programmable data planes also offer high accuracy for certain number of elements. Here I added an accuracy change from tracking network flows with P4 study, where you can see the accuracy is high at certain level. However, as new elements are added to the data structure, the accuracy decreases due to undeletable Bloom filter entries and also limited storage capacity. In other words, Bloom filters are filled up over time. This is the disadvantage of using Bloom filter. To keep the accuracy at a certain level, the size of Bloom filter or the number of hash functions can be increased. This may increase the capacity for a given accuracy, but this cannot solve the filling up over time problem. At this point, since we intend to use Bloom filters data structure for stateful processing of network packets, our research has led us to the following critical question. So each protocol in network is associated with predefined time-out values. So the question is, why don't we construct a data structure that ensures time-based up-to-dateness and efficiently removes the outdated entries? As a result of this critical question, we developed the updatable Bloom filter, as you can see here. In this example, it has 2-bit width, but it can be increased based on your needs. We also added timestamp to each entry, and we changed the logic to add and delete entries to the Bloom array. I will explain this on upcoming slides. Our proposed model checks the up-to-dateness of Bloom filter entries based on predefined epoch time and deletes the outdated entries dynamically. Deciding on the up-to-dateness may vary depend on the application area and desired working structure. So while the Bloom filter original Bloom filter provides high accuracy initially, its accuracy decreases over time due to the accumulation of outdated entries. However, our proposed model dynamically removes outdated entries and sustains the same high accuracy level that original Bloom filter offers only at the beginning. So I want to show you another example for comparison. The left figure shows the accuracy change of original Bloom filter on connection tracking. And you can see that it decreases dramatically even if the array size is comparatively high. But on the right side, you can see that our model has a minimal error size and its accuracy constantly high and does not appear to decrease over time. This is because the proposed balloon filter only stores the status of active connection. Okay, let me take a closer look at how it works. In this example, we have two distinct balloon filter arrays, as you can see, and for each hash functions, and all values are set to 0 at the beginning. Let's assume we have 5 separate connection requests as seen in the right up corner and consider the epoch time to be greater than t value and less than 2t value. At timestamp 0, balloon filter is empty and there is no in data. And at timestamp 1, we inserted the connection 1. We added the value and also timestamp to both arrays. And at timestamp 2, as you can see, balloon filter 1 has a conflict and the data appears up to date. So we subtract the timestamp values and checked if it's greater than or less than the epoch time and decided the up-to-dateness. So in this case, it appears up to date, so we increase the value. At timestamp 3, we inserted connection 3 to balloon filter. Balloon filter 2 array has conflict and this time data appears outdated, so deleting the entry by setting the value 1. Similarly, at timestamp 4, we added connection 4. For this one, there is no conflict. And timestamp 5 at timestamp 5, we inserted connection 5, and both balloon filters appears have conflict, and data appears outdated for balloon filter 1. So we delete the outdated entry, but by setting the value to 1, and we increase the value for balloon filter 2. That's how it works. And the adding and deleting elements on balloon filter can be seen in these flow diagrams. The left diagram shows the P4 program flow while inserting new elements. Basically, the proposed model checks the time-based up-to-dateness of old data and at the points where the incoming data will be inserted. As you can see, the add and delete operations on balloon filter is performed in a single write operation. And there is no need to check the up-to-dateness of balloon filter regularly or with a different mechanism. All is being done dynamically. On the other hand, the outdated data can be deleted in 2 different cases for the UBF. First one is we are inserting any element, as I explained. And second one, if the up-to-dateness of the data can be obtained from the application used, we can delete it from the balloon filter, as you can see on the right flow diagram. Let me give 2 examples to better explain this one. For instance, if you want to track active connection flows on balloon filter, any element can be added upon incoming SIM packet for any connection. And when the FIM packet for connection termination is detected, the previously added element can be deleted from balloon filter. But as another example, if we want to track TCP three-way handshake states against SIM flat attacks, the only way to delete outdated entries is to use the epoch time, as there is no FIM packet or any packet like this one for SIM flat attacks. So this is exactly what we did in our SIM defense study. On this page, I want to present the virtualization of the performance evaluation of the proposed model through an example use case. Essentially, the UBF functions as a rolling window of time, utilizing the epoch time as the size of the window. This way, after one epoch time, a filled-up balloon filter data structure can be considered empty as well. For a new data arriving at time t, data from 1 up to 1 cycle ago is considered up to date. So previously written data becomes outdated. For this example, let's assume that we set epoch time to 15 milliseconds for the stateful tracking of SIM packets. And in this case, we aim to measure the accuracy under a target attack rate of 1 million packets per second. This would require fitting 15K packets per epoch time. However, with the BMV2 switch that we used for testing, which has limited packet processing capacity, it's not possible to handle this much traffic. And essentially, the proposed models behave like the original balloon filter within the same epoch time. Since we cannot increase packet per second rate due to BMV2 switch limitation, we instead increase the epoch time window to raise the number of packets per epoch. As seen in illustration, we increase the epoch time to 150 milliseconds to fit 15 key packets into the single epoch. And so we measured the accuracy variation of UBF data structure, as you see here. As a result, we obtained the accuracy values at varying rates as shown here. On the other hand, the packet per epoch values become more meaningful once the epoch time value for the application use is specified. For example, if we take the 15 millisecond value illustrated in this example, the accuracy variation in tracking SYN requests is obtained as shown here. As you can see, the model provides high accuracy as the array size of balloon filter increases at MPP rates. So up to now, I showed how proposed UBF model works, and after now, I will show 3 different security functions that employ the UBF. The first one is the for the SYN flood attacks. There are 2 typical mitigation and prevention techniques against SYN flood attacks on programmable data planes. First one is the cookie-based SYN proxy, and second one is the SYN authentication, as you can see here. Both approaches may use SYN cookie, which rely on the special selection of initial sequence numbers by TCP servers, but they differ in post-authentication operations. I will not go into detail, but as you can see, both cases require either retransmission or connection resets. But in our compol UBF study, we combined the UBF and also connection pool on the P4 switch and achieved this SYN flood defense technique. In this study, the status of incoming SYN requests is stored in the UBF, and upon verification of the request based on the epoch time, the available resource from the connection pool are allocated. Since there are no protocol violations, connection resets, or additional packet sends, it's completely transparent to the client and server. Besides, in our study, in our approach, there is no such thing as allow listing a verified IP address. Every request made from a given source IP address is treated as unique and is verified individually. So a second use case is for DNS query flood attacks. DNS query flood attacks is a type of DDoS attack targeting DNS servers with the high volume of requests. And this causes DNS server to become unresponsive to requests from legitimate users. So as DNS protocol operates in one-to-one mapping structure, we can easily integrate the UBF to statefully track DNS packets, as you can see here. In other words, although DNS uses the stateless UDP protocol, the proposed approach enables stateful tracking of DNS queries. In this study, we employed UBF to perform stateful tracking of DNS query packets sent to the DNS server and their corresponding response statuses. And another mechanism is the token bucket. Token bucket is a method employed to rate limiting the bandwidth or the number of packets at network layer. And inspired by the token bucket approach, we implemented a similar method to apply rate limiting for active DNS queries using the P4 language, as you can see here. We propose a modified token bucket approach in which a token is added upon a DNS query and any token is added upon a DNS response. Basically, the status of each DNS query from the client is stored in the UBF, and when a DNS query received, index values are calculated using 4-tuple data as input for hash functions, and then the data is then written to the balloon filter. The use of 4-tuple is motivated by the fact that the different DNS requests from the same client are stored in the same bucket of the balloon filter. The status information for active DNS requests is maintained per client IP address, and response packets are received from the DNS server. after response packet is received from DNS server, this data is removed from the UBF, I mean. So concurrent multiple DNS queries can be originated from the same client, as you can see here, and these multiple queries can be stored in the same bucket. As we can now statefully track DNS queries, we can implement a rate limiter against DNS flood attacks. For instance, the number of active queries per client can be limited by choosing an appropriate concurrent query limit value. This figure here illustrates an example of working structure when this value is set to 3 in the proposed method. On the other hand, the proposed approach monitors DNS requests initiated by the client that are still pending a response from DNS server. The proposed approach from this point of view dynamically adapts to the server backlog status by tracking and limiting active, not yet completed queries. Also, applying client IP-based rate limiting prevents attacker from consuming excessive DNS resources, especially in flood attacks. This ensures a more fair distribution of server resources among clients. So detailed flow diagram for algorithm of P4 program can be seen here, which combines the UBF and token bucket. The epoch time of DNS packets are referred to as DNS timeout, which specifies the time threshold for retaining DNS queries in the UBF. The flow diagram on the left side demonstrates how DNS queries are dropped or forwarded based on the rate limiting conditions. Similarly, on the right side, you can see how it removes elements from UBF when receiving a DNS response packets. In the proposed approach, rate limiting is implemented in 2 distinct levels. First, rate limiting per client IP, and second one is the total concurrent query rate limiting. So regardless of the scale of the DDoS attack, you can limit the total concurrent queries at network layer as well and avoid DNS server become unresponsive. Besides, we can also detect certain attacker behaviors using the proposed rate limiting approach and also punish them for a period. As you know, in the UBF, the timestamp was employed to verify the up-to-dateness of data by calculating the time difference. However, the timestamp value can also be utilized for punishing any attacker for a certain period and also measuring inter-query time per client to detect flood attacks. And achieving this is possible in the current approach by only adding a few additional controls, as you can see in this flow diagram. Let me explain how it works over a timeline. Normally, if we receive a data at time T2, we subtract T1 from T2 to check the up-to-dateness. And let's assume we decided the punishment at time T. Subsequently, if we write T plus TP value, TP is being the punishment time, into the bucket on Bloom filter, the resulting TSDiff values for all requests from the same client during the punishment time will be negative. For example, TSDiff is negative for the time at time T. In the light of this situation, incoming requests during the period when TSDiff is negative can be blocked with an additional control. This way, UBF also provides the punishment. On the other hand, as timestamp value contains the timestamp for the latest DNS packet processed from the same client, the time difference also gives us the inter-query time. For this reason, if TSDiff value is greater than 0 but less than the inter-query time threshold value, the corresponding IP can be similarly punished for the punishment time period. So this approach also offers several critical advantages over the traditional method of block listing IP addresses. So in the traditional approach of adding an attacker IP address to the block list, this may lead to insufficient switch capacity as the number of IP addresses increases. And additionally, since this process needs to be executed by the controller, the additional time may increase depending on the density of the attackers. However, the proposed approach here leverages the existing UBF data structure, and it eliminates the need for additional storage space. Also, the proposed approach does not require a separate process to end the punishment time and delist the IP address. Okay, let me show you here the rate limiter results briefly. The rate limiting approach was tested against both authoritative and recursive DNS servers. The test results demonstrate that while the success rate of attacker queries increased with the use of more IP addresses for the same volume of attack traffic, the number of dropped attacker IP address has significantly risen over time. If we compare both set of results, it becomes evident that the rate limiting approach is more aggressive for recursive name servers. This is because of the increased backlog in recursive queries. And as a result, this leads to quicker punishment applied to IP addresses of attackers. This outcome highlights how the proposed approach adapts to the DNS server's backlog load and its responsiveness to DNS queries, applying it to varying number of attackers. And DNS firewall is the final use case. As illustrated here, DNS amplification attacks are conducted by sending a high volume of DNS requests with spoofed source IP address to open DNS servers. This causes DNS servers to send amplified DNS response traffic to the victim, overwhelming its resources. The attack is conducted through the spoofing of target system's IP address, and DNS responses generated substantially exceed the size of original DNS request. That's why it's known as amplification attack. As you can see here, by adopting the one-to-one mapping approach, we explored another set of ideas and developed a novel DNS firewall. First, we considered using DNS transaction ID in addition to IP and port numbers to enhance DNS query tracking performance. This approach enables stateful tracking at the application layer, addressing scenarios where high volume attacks might allow some requests to reach the victim if only IP and port numbers are used. As illustrated in the figure, each DNS query sent by victim is inserted into Bloom filter, and upon receiving the DNS response to this query, the response is verified through the UBF and subsequently deleted. As the proposed DNS firewall works at application layer, it can block all the unsolicited DNS responses, but there is a requirement in this approach, which is the spoofed DNS queries do not pass through the point of detection. For instance, if the source of the attacks is within the ISP's own network, or the requests that initiate the attack pass through the same leaf router that we use for detection, they cannot be separated. Okay. Another challenge of DNS firewall is the fragmented DNS response packets. We also needed to statefully track them. Extension mechanism for DNS, known as eDNS0, enables a DNS server to send large DNS response through IP fragmentation. Therefore, in response to a DNS query consisting of a single packet, fragmented DNS responses consisting of 2 or more packets can be received. As a result, fragmented DNS responses do not adhere to one-to-one mapping. Moreover, reported real-world amplification attacks are often characterized by their massive scale, with volumes reaching terabits per second rates, largely due to the use of eDNS0. Therefore, it's essential to statefully track the fragmented packets as well. As a solution, a second UBF was created to track DNS fragmented packets, named FragmentBF. It's a dedicated data structure serving as a block list for fragmented DNS amplification attack packets. As the upper headers only appear in the first fragment in IP fragmentation, as you can see from the flow diagram, we utilize the first fragment packet to detect fragmented DNS responses and classify them. In this case, FragmentBF can retain the data of an incoming fragment packet for 1 epoch time. The inter-fragment time value was measured as 7 microseconds in our test, which means the time between the first and last fragment packets of a fragmented DNS response. In this case, the epoch time value can be set higher than this value, for example, 10 microseconds. And utilizing a very low epoch time values enables temporal tracking of high volume packets with a UBF of minimal size. This way, legitimate fragment packets are not blocked. And here I want to show you the accuracy of the UBF for DNS amplification attacks, where the DNS response packets are fragmented. This performance efficiency highlights the potential of proposed approach to mitigate high-volume DNS DDoS attacks with minimal resource overhead. Additionally, the accuracy of the proposed method is directly linked to the size of the updatable balloon filter it employs. To address increasing demands, the size of this data structure can be scaled in accordance with the memory resources and constraints of the P4 hardware, ensuring adaptability and scalability to meet the evolving requirements. You can find comprehensive details in our Help for DNS study. So on this last slide, I want to summarize how we have applied the UBF balloon filter in practice. We first used it to track SIM packets during the TCP three-way handshake, ensuring accurate stateful monitoring. We then applied it to adaptive rate limiting of DNS queries and also to one-to-one mapping-based tracking of DNS packets. Another important use case is the tracking of fragmented DNS responses, which is critical for defending against amplification attack. Additionally, UBF allows us to implement time-based punishment for attackers and to measure interquery times effectively. These examples demonstrate the versatility of UBF in addressing different network security challenges. What makes our proposed UBF especially powerful is that it remains simple in design, efficient in execution, and robust against various of attack scenarios. In other words, it delivers strong protection without adding unnecessary complexity. Thank you very much for listening to me. That's all.
Awesome. Thank you very much for the super interesting presentation, Mehmet. I have a few questions for you. So you showed basically the system working with three specific use cases, which is great. But I'm thinking about as an operator, if I want to use it, I want to understand, like, is this extensible? Can I use it for many other type of use cases? What are the type of, let's say, use cases that more fit your data structure and which are not, right? So.
Yes, of course. The key point is that the UBF provides both time-based up-to-dateness and stateful traffic tracking. Since all network protocols have their own states and timeouts, whenever a protocol is found to be vulnerable to a certain type of attacks or a security function can be developed using the UBF. For instance, we demonstrate this for DNS flood attacks, but a similar approach could be applied to HTTP flood attacks or slow HTTP attacks. Or even there are some other type of amplification attacks as well. You may know NTP attacks or memcached.
Do you think also one of the attacks that I see like recently a lot are like spikes type of attacks where you send like spikes to try to, let's say, for a short amount of time to basically try to let's say finish all the resources of a specific server? Or do you think that this would be probably in your case a method to adapt a little bit more the timeout of your system, so the configuration of your system? Is that correct?
Yes, that's right. In our DNS study, as you can see, we were tracking the DNS queries and responses on the P4 switch dynamically and rate limiting the queries. So for your question, you can limit the queries or traffic based on the source IP address, and it limits it to consume too much resources from the same IP address. They cannot make spike requests as you mentioned.
Okay, no, that makes a lot of sense.
Yeah.
Another question I have is generally, like, when I'm thinking about bloom filters, are like data structure that they might be vulnerable to target set coverage. And I
Mhm.
wonder if you have any insights on how your, let's say, UBPF would work in this specific case.
Yeah, this is a good question. To improve the security, there are some known methods such as use of salted inputs or key hash functions against target set coverage attacks. As for the UBF, the input data is critical against this kind of attacks. So in our implementation, UBF allows us to use salted inputs. For instance, we used 5 parameters: source IP, source port, sequence number, egg number, and protocol as inputs for balloon filter validation for the SYN attack example. The sequence number value here was generated by the P4 switch and can be treated as salted input. This is because this value was determined based on the arrival time of packet to P4 switch measured in microseconds. Since the arrival time of a packet in microsecond resolution is subject to various variables in the network, you can treat it as salted input. Furthermore, even if a collision condition occurs in UBF for some reason, if you don't use the salted input, its validity is limited to a single epoch time due to nature of the UBF. So you can consider it as a robust against target set covered attacks by design. Yeah.
That makes sense. Thank you very much. I have one last question. When I was sorry, when I was listening to your presentation, it made your data structure made me think a little bit about. I don't know if you haven't encountered them, but you know, there are like a data structure called the time decaying Bloom filters, so that they are Bloom filters that they kind of decay with the time. And there is a sort of some research paper that they try to explore these research line and this data structure. Now, in a sense, you know, when I'm thinking about your data structure, in some sense, this is similar to what you know, at least the overall idea is what is there, right? So, and I wonder if you had the opportunity to consider also that this other type of data structure, if your decision was to design a completely new data structure for any other reason. And I'm just curious about, you know, if you have already started comparing or not. And, you know, I'm just curious to understand a little bit better the space here.
Yeah, as for the data structure, actually, we did not switch to the area that we compare the data structures and other use cases. We more focused on the security functions here. So there was a security problem here we are handling, and we try to implement an efficient data structure. I mean, rather than comparing other data structures.
Okay, no, that makes a lot of sense. Then you know, this I think concludes the talk. And thank you very much for your time. Thank you very much for your great talk. And you know, hope to see you soon.
Yeah, thank you very much for listening to me. It was a great chance for me to present my study.